My name is Paul Lenz, and today we're going to talk about some trigonometric functions, the sine, the cosine, and the tangent. Trigonometry is the use of finding lengths or angles of any particular triangles. But the use of the sine, the cosine, and the tangent, we have to determine that we're dealing with a right triangle, or in other words, a triangle of 90 degrees. Where does it have use? In the area of physics or engineering, and such things as velocity, torque, and acceleration all can be used with these trigonometric functions. How do we define sine? Now, sin is pronounced sine, it's not sin, and it's defined as the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. There are three other values which you don't see on your calculator. The sine, cosine, and tangent are. Those happen to be the secant, the cosecant, and the cotangent. What they are is inverse. Now if we look at a drawing which has in this case the value of A and B and C, we're going to see these values. When we talk about the sine of A, where A is that value, normally the angles are in capital letters, the sides are in lowercase letters. If I talk about the sine of A, I would say that the sine of A is the opposite, and there we have the opposite over the hypotenuse, and the hypotenuse in this case happens to be C. So we're saying that the sine of A is equal to, in this case, A divided by C. We could also say, what happens if I go to angle B? All right, well in angle B, if I have the sine of angle B, that means that B in this case happens to be the opposite. It's the opposite value. So we're going to say the sine of B is equal to, again, B divided by C. Now, does that mean that A is always the opposite? Well, no, in some cases it could be the adjacent, because if we would say the cosine of B, well, the cosine of B would be the adjacent, which in this case happens to be A, so now I have A divided by C. So we have to remember which particular angle we're dealing with when we think about what is the opposite, what is the adjacent, and of course the side opposite the 90-degree angle is always the hypotenuse. When we have an angle of elevation and an angle of depression, they actually happen to be equal to each other. The reason is the two lines are parallel, and what those angles are, they actually happen to be alternate interior angles, if you remember from your geometry. If we take a problem where a plane is flying at 2,000 feet and the angle of depression to the airport is 23 degrees, we could ask two questions. How far is the plane from the airport? And also, how far does the plane have to fly in order to land at the airport? Now, the first one is how far is the plane from the airport? That happens to be D1. So we would take the tangent, which is defined as the opposite over the adjacent, and we would say that the tangent of 23 degrees is equal to 2,000 divided by D sub 1. We then would say D sub 1 is equal to 2,000 divided by 23, and if you put that on a calculator, you would have 2,000 divided by the tangent of 23, and that is approximately 4,712 feet. To find D sub 2, which is actually how far does the plane have to fly in terms of distance, we would say the sine of 23 degrees is equal to 2,000 divided by D sub 2. D sub 2 is equal to 2,000 divided by the sine of 23, or approximately 5,119 feet. Now the next one would be, in this case, where we have a pole in a parking lot. This pole happens to be 50 feet high, and the guy wire is anchored in the parking lot 32 feet from the base of the pole. We would like to know how far is that guy wire. Well, in this case, we have a tangent is equal to 50 divided by 32. Now, we can't just hit that value. We need to, on a calculator, hit second tangent, which means I am now finding an angle. And you have to make sure that your calculator is in degrees rather than radians. To do that, you need to hit the mode key, and that will show you whether you're in degrees or radians. From that standpoint, we now have arctangent of 50 divided by 32, and that would give us, in this case, 37.38 degrees. We would like to show you the keystrokes necessary to find the angle from the prior problem. In this case, we need to find the inverse tangent. When we push inverse tangent, we need to hit the key second and then tangent, and that becomes inverse tangent. And then we need to put the two sides in this case, 50 divided by 32. We need to close this with a parentheses, and then we need to hit enter. And that's how we arrive at that angle of 57.38 degrees.
Thanks, Paul. Hi, I'm Margie Coleman. Now that Paul has introduced right triangle trigonometry, let's talk about trig values for some special angles. Our first special triangle is the 45-45-90 triangle. Let's find common values for the lengths of the sides. Assume one leg of the triangle has length 1. Since these angles are congruent, the other leg must also have length 1. Now we can use the Pythagorean theorem to find the hypotenuse. 1 squared plus 1 squared equals the hypotenuse squared. Let's just call it c. So 1 plus 1 equals c squared. So if 2 equals c squared, then c is the square root of 2. Now let's find the values of sine, cosine, and tangent for the angles in our 45-45-90 triangle. If we focus on this 45-degree angle, then this is the side opposite that angle, and this is the adjacent. Now recall the sine, cosine, and tangent ratios. So the sine of 45 degrees is equal to its opposite over its hypotenuse. We often choose to rationalize the denominator when we have a fraction with a radical in the bottom. To do that, we would just multiply the top and bottom by radical 2. 1 times radical 2 is radical 2. Radical 2 times radical 2 is just 2. So the sine of 45 degrees can be called 1 over radical 2, or it can be radical 2 over 2. Now let's look at the cosine. Cosine is the adjacent side over the hypotenuse, which again can be written as radical 2 over 2. The tangent is the opposite side over the adjacent side, and 1 over 1 is just 1. Let's find out what happens if we have a larger or smaller 45-45-90 triangle. Suppose the two equal legs are length 2 instead of 1. Since trig values are ratios of the sides, and similar triangles are proportionally similar, the sine, cosine, and tangent of an angle will always be the same, no matter how big we draw the triangle. By the Pythagorean theorem, we have 2 squared plus 2 squared equals c squared. So 4 plus 4 equals c squared. Therefore, c squared equals 8. So c is the square root of 8. And if you remember how to simplify a radical, we can rewrite square root of 8 as the square root of 4 times the square root of 2, because the square root of 4 is just 2. So we can write the hypotenuse now as 2 radical 2. So let's find sine, cosine, and tangent again using this triangle. Again, if this is our angle, the sine of 45 degrees is the opposite side over the hypotenuse, and our 2's cancel, leaving us 1 over radical 2, which we found out a few minutes ago is the same thing as radical 2 over 2. The cosine of 45 degrees is going to be the adjacent side over the hypotenuse, which also simplifies to 1 over radical 2, or radical 2 over 2. Now the tangent would be the opposite side over the adjacent side, which again equals 1. Notice that these are the same values. Our next special triangle is the 30, 60, 90 triangle. Let's find common values for the lengths of these sides. Let's start with an equilateral triangle with sides of 1 unit. So all 3 sides really are 1 unit. Now drop an altitude. That cuts the base into 2 equal pieces. So focusing on the right side, we have a small right triangle with a base 1/2 and a hypotenuse 1. Since the original triangle was equilateral, you will remember from geometry that this angle must be 60 degrees. And the top angle was cut in half, so this angle is 30 degrees. Now we can use the Pythagorean theorem to find this other leg of our right triangle. So I have a squared plus 1/2 squared equals 1 squared. So a squared plus 1/4 equals 1. Subtracting 1/4 from both sides, we get that a squared equals 3/4. So a is the square root of 3/4. And when I take the square root of a fraction, I just need the square root of the numerator divided by the square root of the denominator, which is just 2. So our third side then is radical 3 over 2. Now let's find the values of sine, cosine, and tangent for the angles in our 30, 60, 90 triangle. Let's start with the 30-degree angle, which is here. Then this is the opposite side, and this is the adjacent side. So the sine of 30 degrees equals the opposite divided by the hypotenuse, but divided by 1 just leaves me with what I started, so it's just 1/2. Now the cosine of 30 degrees is the adjacent side, radical 3 over 2, again divided by the hypotenuse, which is 1. The tangent of 30 degrees is the opposite divided by the adjacent. So I want to simplify this complex fraction. We take the 1/2, and dividing by a fraction is the same as multiplying by its reciprocal, meaning flip that over. Now my 2's cancel, and I have 1 over radical 3. And some people use that to represent the tangent for 30 degrees, but sometimes we want to get the radical out of the denominator. So again, I can multiply the top and bottom both by radical 3, and I get radical 3 over 3. Now let's look at the 30, 60, 90 triangle from the perspective of the 60-degree angle. So if this is our angle, then this is the opposite side, and this is the adjacent side. So now the sine of 60 degrees is radical 3 over 2 divided by 1. The cosine of 60 degrees is 1/2, again divided by 1. And the tangent of 60 degrees is radical 3 over 2 divided by 1/2. Again, we'll simplify this complex fraction by taking radical 3 over 2 times the reciprocal of 1/2, which is 2 over 1. My 2's cancel again, and I'm left with radical 3 over 1, which is just radical 3. Today, you learned about right triangle trigonometry, and then we talked more about some special right triangles and the sine, cosine, and tangent values for their angles.